So this is the third talk of the lecture series on decomposition theorem for singular varieties with C1 equals 0. And I will speak about the positivity part of the proof. And so this is going to be about, say, vector bundles with C1 equals 0. Okay. And so everything is going to be over C. And okay. And so that in order that you see the relation of this talk to what has been happening this morning and what will come the next 2 days, let me start with a statement about algebraic integrability of foliations. And this is somehow a line of work initiated by a famous paper of Bost. Then there's another paper, much more recent, by Campana and Paun. And the version which I will present here is due to Stéphane Ruel. And so it's Ruel's formulation which actually will be useful for our context. Okay? So I take X, a normal projective variety, and on this variety I take some foliation. Okay. And now I make an assumption on the positivity of this foliation. I suppose that the dual of F, this is going to be some reflexive sheaf, and I suppose that this is not pseudo-effective. Okay. And then the conclusion is that this foliation has algebraic leaves. Okay, so then F has algebraic leaves, or to be more precise, it's algebraically integrable in the sense in which Carolina defined it. Okay, so then under this positivity assumption, the foliation is algebraically integrable. So if you take a general leaf and you take its closure, then this is going to be a projective variety having the right dimension, meaning the rank of the foliation. Okay, and so somehow, no. This is this statement is correct, I think, and I will come to C1 equals 0 in a minute. Okay. So that's the statement, and if you think about the lecture this morning, somehow in the line of the proof of the Beauville-Bogomolov decomposition, there was this Chiga-Gromov theorem which said that the factors which are non-Euclidean, they are compact. Okay, and so somehow this will play an analogous role. So somehow here you have a foliation with algebraic leaf, and so this corresponds to these compact factors in the decomposition. Okay. Now I have to tell you what I mean by this assumption, and I will give the definition of being pseudo-effective or not in the case where it's a vector bundle, and the general case, takes a bit more work, but it's not very enlightening actually. Okay, so what does it mean to be pseudo-effective? So if I take V over X, a vector bundle over a projective variety, X, okay, then I look at the tautological class on the projectivization. Okay, let zeta over P of V be the tautological class. Tautological class. Okay, so tautological meaning that zeta, that's the first Chern class of the tautological line bundle on your projectivization. And then I will say that this vector bundle is pseudo-effective, well, if the tautological class is pseudo-effective. Okay? B is pseudo-effective if tautological class is pseudo-effective. Okay. Okay, so you see, I make this definition so that it's analogous with the definition which we traditionally make for NEF or ample vector bundles. Okay, you say that a vector bundle, it's NEF or ample if the tautological is NEF or ample. Okay, so it's exactly the same spirit, although in the literature some people define pseudo-effective vector bundles in a different way, but for our purpose, I think this is the good definition. Okay, and so this is for a vector bundle. You just reduce to the tautological class, and so if you have a reflexive sheaf, then you have to make a different, somehow an equivalent property in terms of vanishing of some symmetric powers. Okay, so we mark for reflexive sheaf. We use some equivalent definition in terms of symmetric powers. Definition in terms of sections of symmetric powers. Okay. Symmetric powers. Okay, so so this is a bit more work, but in the end, for what I will prove, understanding the vector bundle case is quite okay. So, so now we know what the assumption means. How do you check it? Okay, so how to check if this dual of F is pseudo-effective. Okay. So I will assume for simplicity's sake that F is stable with respect to some polarization. Okay. Otherwise, the statement is a bit more. Statements are going to be a bit more complicated, but can be formulated. But as you saw this morning, somehow in view of what we want to do, it's stable vector bundles that we're interested in. Okay. So assume F is stable with respect to some polarization, H. Okay, and if you don't like to work with just polarization, you can also formulate this for movable classes. I mean, there's been quite some activity around this for some time. And now, so I assume this, and then somehow one way to check this condition that F star is not pseudo-effective is to look at the slope. Okay, so slope condition. So if the slope of F, this is positive, well, then F star is not pseudo-effective. Okay, let me abbreviate pseudo-effective by psef. And so this slope condition, I mean, this can easily be computed. You just take the determinant of F times. So let me say variety of dimension n. You check if this intersection number is strictly positive, and you're done. Okay, assuming stability. Okay, and so this is somehow the kind of setup that people have been working in for quite some time. So this, this work of Bogomolov and McQuillan, and this is also the kind of condition that appears in the Campana-Pound theorem. And so this is this point, of algebraically integrable foliations such that the leaves are even rationally connected. Okay, so this is a line of work which has been going on for some time, but as you can see, if the determinant of your foliation is 0, numerically trivial, then certainly the slope condition won't help. Okay, so slope condition does not apply in the case C1 equals 0. Does not apply to case C1 of f equal to 0. Okay, there's no hope to do anything with this kind of a condition, and for good reason, because if you have, say, a vector field on some variety, okay, so this is going to be your f, and then certainly f star is pseudo-effective, and in general vector fields are not algebraically integrable. So certainly for C1 equal to 0, you cannot hope that always f star is going to have this property of not being pseudo-effective. Okay, certainly for vector fields, this does not work. On the other hand, we know some vector bundles with C1 equals 0 which are not pseudo-effective, and so somehow the classical example is the tangent bundle of a K-free surface. Okay, surface. This is not pseudo-effective. Okay, and if I say classical, I mean this was shown independently by Nakayama and Buxom, Demailly, Pound, Péternel around 2004. Okay, so here we have an example of a vector bundle with C1 equals 0, but it's not pseudo-effective. Okay. And so here comes the result, which I proved with Thomas Péternel 2 years ago. So let X be a projective manifold. Yeah. Yes. It has. Yes. If it does not vanish in codimension 1, then it defines a proper foliation, which typically is not algebraically integrable. Yes. Is this okay? Okay. So let's take a projective manifold, and V, a vector bundle on X, such that the first Chern class is equal to 0. And now come the assumptions. So I assume that all the symmetric powers of V are stable. Are, say, H stable for some polarization H. First assumption. And then the second assumption is this vector bundle is pseudo-effective. Okay? Now, if V is pseudo-effective, well, then V is Neff. Okay? So that's the statement, and let me make some remarks, comments. Okay. So remarks. So so for simplicity's sake, I wrote it like this, but you know, can generalize with this statement. You know, statement is true in some you know, in some appropriate sense, that if X is no longer a projective manifold, but X is projective, KLT smooth in codimension 2. And of course, I don't want to have vector bundles, but V reflexive sheaf is also okay. Okay, so somehow the kind of setup which is useful for the decomposition theorem we're aiming at certainly holds in this kind of generality. That's first remark. Second remark is that so somehow if you formulate it like this, you see that, you know, you have this property, this positivity property of being pseudo-effective, okay, which is kind of nice and says that somehow on many curves your tautological class has non-negative degree, and then you get the stronger property that actually on all curves the tautological class has non-negative degree. Okay, so that's obviously better, but still, how do you check? How do you check if someone is Neff or not? Okay, and then there's the following useful fact: if you have a vector bundle which is Neff with C1 equal to 0, well, then the second Chern class is also equal to 0. Okay. And so this is something which you can easily check in practice. So let's say corollary: if I take X, a projective manifold, and I take F in Tx a foliation such that all the symmetric powers are H stable, such that all these symmetric powers are H stable. Well, then if the first Chern class of F is equal to 0, but the second Chern class of F is not 0, then this foliation is algebraically integrable. No, has algebraic leaves. Okay. And why is this an obvious corollary? Well, somehow, since in view of this, if the second Chern class is not 0, but C1 is equal to 0, this tells you that the vector that F dual is not going to be Neff. If it's not dual, thanks to the theorem, it's not pseudo-effective. But if it's not pseudo-effective, well, then you can apply this statement. Okay? Yes? Okay. So for a vector bundle, there is no difference. And for a reflexive sheaf, so if you have F, a reflexive sheaf, then, if I take a symmetric power, then this can be, it can be some weird stuff. So in order to eliminate the weird stuff, I take the bidual so that I get a reflexive sheaf, and then I call this S bracket of F. Okay? Okay.
So I have a question. So in your theorem with torus, so the conclusion is D is numerically flat.
Yes. In fact, it's numerically flat, yes. Yeah, exactly. Okay. Oh, yes. So the assumption, of course. So somehow there's this assumption which is around here all the time. I mean, obviously, this is a strong assumption, and you cannot check this as easily as just stability of the vector bundle itself. But thanks to the work of Grip, Genancia, and Québecus, we know that this is true for the foliations which we're interested in for the decomposition theorem. Okay, so this is the corollary which was on the blackboard just at the end of the lecture. So we know that in the setting where we want to work, this is true. Okay, so this is why somehow it's natural to put this hypothesis. And let me say that the statement is not true if you just assume V to be stable. Okay, I mean there's a counterexample which appears in the paper of Stefan, and so stability just for V is not enough. You can improve a bit. You know, there are. It's enough to assume stability of some sufficiently high symmetric power, but well, you know, in practice, all these kinds, this stuff is hard to check. Okay, and maybe one final remark. So if you don't like the proof which I will present right now, you can look at a different proof using positivity of direct images by Zhao, Campana, and Paun, which appeared on the archive last week, and they even do it for smooth compact Kähler manifolds. Okay, so remark. So recent preprint. So extend this to the Kähler case, the theorem to the Kähler case. Okay, but they only, well, unfortunately, I would say, they only extend this theorem, not this one. Okay, so it makes perfect sense to write down this statement and replace normal projective variety by normal compact Kähler space, and the same should be true, but we don't have a proof of this. Okay, that would be extremely nice, but certainly not today. So now, are there any questions about what I said so far? Okay, now, so here comes the fun fact. So this is a statement on, you know, high-dimensional algebraic geometry, but actually, basically, it boils down to a lemma for vector bundles on curves. Okay. So somehow key lemma. Let's see, be a smooth curve. Smooth curve. No, and I mean for me it's always, you know, projective curve, and I take V over C, a vector bundle with C1 equals 0. And again, I put the assumption that all the symmetric powers are stable. Stable. And now I take a subvariety of the projectivization. Okay, so at Z, subvariety of the projectivization, but not the projectivization of V itself. Okay, subvariety. Then one has the following property. If I take my tautological class and I intersect it with the subvariety, so I compute somehow the degree of my tautological class on the subvariety, well, this is strictly positive. So that's the lemma, and let me. I mean, some people were already here in week 1, and so let me recall an example which we saw in the first week, and maybe those who weren't here will know this example anyway. So there's this example of Mumford of a line bundle L. Line bundle L on a surface X, such that, well, the intersection of the line bundle with any curve is strictly positive, okay, for all C in X curve. Okay, so in particular, this line bundle is nef, but L is not ample. It's not ample, and well, why is it not ample? Well, actually, L square is 0. Okay. Okay, so we saw this example in week 1, and this shows that in order to check amplitude of a line bundle, it's not enough to check on curves. Okay, you need to take all the intersection numbers which appear in the Nakai-Moshizon criterion, and the construction of Mumford is exactly of this type. Okay, so Mumford's example is of this type, meaning he takes some rank 2 vector bundle with C1 equals 0, having this kind of stability property, and then shows that the tautological class, this is going to be L. Okay? Okay, so somehow this lemma is a generalization of this famous example of Mumford, and somehow the key point why things behave in this kind of pathological way here is that this line bundle, it's nef, but its Kodaira dimension is minus infinity. So somehow the key point of the construction is that no multiple of L has global sections. Okay. Okay, and so we'll see in the proof of the lemma that as soon as your line bands start to have global sections, things become much easier, and you can prove this kind of statement. Okay. So that's the reminder, and now let me remind you some standard facts about vector bundles on curves, which we're going to use. Okay, so reminder about vector bundles on curves. Okay. first thing is statement, well, which I think is due to Miyaoka, is that if you have, so I will always have V over C, a vector bundle on a curve. And so if V is semi-stable, and first Chern class of V is 0, then V is NF. Okay?
If x squared is 0, h0 of x12 should be C10.
Why should it be? Why should it have a global section?
Oh, because it's projective x over.
No. This is not the tensor power. That's that's the intersection product. Sorry. So C1 of L squared. Okay, I'm sorry. Okay, so if you're semi-stable with C1 equals 0, then V is NF. So here in this assumption, we certainly know this. So the tautological class is going to be NF. Okay, so certainly we know that this intersection number is going to be non-negative. Okay, but as you see, somehow we want strict positivity, and this is really the key point. Now, so this first statement. Second statement is Hartshorne's criterion for amplitude of vector bundles. So Hartshorne's criterion. If you take W over C, a vector bundle, then this is ample if and only if for every quotient, so you take a quotient vector bundle Q, and the condition is that the degree, so the first Chern class of Q, is strictly positive. One has C1 of Q strictly positive. Okay, so that's Hartshorne's criterion, and one has to be careful. Important, when you look at all these quotients, be sure to include the trivial quotient. Okay, this includes the trivial quotient. Where Q is equal to W. Okay, so in particular, this is the kind of property. So in particular, you need C1 of W is strictly positive. So this is exactly the kind of property which our V here does not have, and this is somehow why it's a challenge. Okay. Okay, so this is Hartshorne's criterion. Okay. Okay, and now let me put these two things together. So consequence, if I have, my vector bundle, my symmetric powers, which is stable with C1 equals 0, so this is a vector bundle which is NF but not ample, then any non-trivial quotient will be ample. Okay, then any non-trivial quotient. Okay, so not the quotient of this vector bundle by itself. This is ample. Okay. So let me, this is easy, but still, let me do this. Okay, so proof. Okay, so so I want to apply Hartshorne's criterion. So if I take any quotient of W, then I compose this. So this is then now, so this here is now a non-trivial quotient. It's a non-trivial quotient. But by stability, this tells you that the slope of Q has to be strictly larger than the slope of your vector bundle SLV. And this is 0. And of course, I mean, this is just C1 of Q over the rank. So you see that that this is strictly positive. Okay? Is this okay? Okay, so this is somehow the specificity of these vector bundles, which are stable with C1 equals 0. They are Neff, but not ample. But as soon as I take some non-trivial quotient, I will get some ample vector bundle. This is somehow the trick. Okay. Sorry?
I don't understand why you wrote two lines there. If omega and q and then.
So I want to apply Hartshorne's criterion to the vector bundle W. Okay? So I have to look at any quotient of W. Any quotient of W defines a quotient of this vector bundle which is not trivial. Okay? Okay. No questions? Okay. So then we can prove the key lemma. So proof of lemma. Okay. And so let me somehow set up a bit the notation. So I have the projectivization of my vector bundle. And in here, I have my subvariety Z. And so this has a map to C, which I will denote by phi. And so this is just the restriction of pi to Z. Okay. And let me say, if Z is a curve, then if you look at the proof of Mumford's examples, you will see that it works. That the proof of Mumford actually works in this setting. So it does not really depend on the rank of the vector bundle. So somehow in your mind you should think that this is a variety of dimension at least 2, and I will show you how to reduce the problem to curves. Okay, and for curves it's already known. Okay, so this is first remark, and then somehow this map here, obviously if this, I can assume that this is surjective, because otherwise if Z is contained in a fiber of the projection, well, the tautological is ample on the fibers, so there's nothing to prove. Okay. Okay, so this is our situation, and now let's try to analyze this. And what we do is we start with the ideal sequence of Z in the projectivization of V. Okay, so I have this ideal. I have a structure sheaf of P of V, and I have the structure sheaf of Z. And now I twist this with some multiple of the tautological line bundle. Okay, so twist with some multiple of the tautological line bundle. Okay, so I get sequence which I will write like this. Okay. Okay. Now, as I said, so this line bundle, this is Neff, but I know a bit more. This is relatively ample. Okay, it's relatively ample. So I can apply Sayre's criterion. Tell me that for L large enough, the direct image of this ideal sheaf twisted with L, this has positive rank. Okay, so somehow if you take L high enough, you will find hypersurfaces of degree L which cut out Z in the fibers. So this is positive rank, and if I look at the first higher direct image, this is going to vanish. Okay, so this is relative zero vanishing. Okay, so this I know for L sufficiently high, and now I push down this sequence. I push it down onto C. Okay, push onto C, and then what do I get? So I get push forward of this ideal sheaf. When I push forward L times the tautological line bundle, I obtain this L symmetric power of V. And then if I push down this guy, well, I will obtain its push down. Okay, and here now comes, here comes the R1 I've been talking about. And this is 0 by my construction. Okay? So what do I have? I have here my stable vector bundle with C1 equals 0. This has positive rank, so this is a non-trivial quotient. Non-trivial quotient. Okay? So by what I said in remark 3, this is an ample vector bundle. Okay. Okay. Okay, so this vector bundle is ample. In particular, some symmetric power of it will be globally generated. And this is good because this is the kind of property which behaves well under pullback. So now I pull this back to my variety Z. Okay, so this is ample. So if I pull it back, it might not be ample, but it's still semi-ample. And this has this natural surjective map to the line bundle I'm interested in. Okay. And since this is semi-ample, this is also semi-ample. Okay. And by semi-ample, I mean some multiple is globally generated. Okay. So here you see the difference between what is happening on the subvariety Z and what happens in the Mumford type example. Here in the Mumford type example, I have a line bundle which looks quite positive, but it does not have any global sections. Here I have a line bundle which also looks quite positive, but even better, it has a lot of global sections. Okay, it's globally generated. Okay. Well, if it's globally generated, then it defines a map. Okay. So let me say this is already globally generated to make the notation a bit simpler. So I will get some map defined on Z to some base B. And so this is the morphism. So this is the morphism defined by this line bundle. Okay. Now here comes the point. Assume that this number is 0. Okay. Okay. So recall that this is the first Chern class of O of 1. So this is actually, this is the first Chern class of this guy up to multiple. So if this is 0, then this means that this line bundle, which is globally generated, is not big. Okay, so this maps onto a variety of strictly lower dimension. Okay, then B has strictly lower dimension. Okay. In particular, I have positive dimensional fibers. But if I have, but in these fibers, there are many, many curves, and on these curves, I'm 0. Okay. Then a curve C in the fiber has zeta times C equals 0. Okay. So you see, I started with any subvariety in P of V, and somehow the argument is that if things go wrong, things already go wrong at the level of curves. But Mumford already told us that things will not go wrong if you have this hypothesis. Okay? So that's somehow the proof. Okay. So are there any questions about this proof? Yes. Sorry?
Which assumption implied that the intersection?
We already know that the vector bundle is Neff. Because already, this is Miyaoka. You're semi-stable with C1 equals 0, so you're already Neff. Okay? Are there other questions? Okay, so then I have 10 minutes to indicate why this lemma is useful to prove the theorem. Okay? Okay, so how to use the lemma in the proof of the theorem. Okay. So statement is here. So the assumption is the vector bundle is pseudo-effective. So by assumption, my tautological class zeta is pseudo-effective. Okay. And for these pseudo-effective divisor classes, we have what is called divisorial Zariski decomposition. Zariski decomposition, which tells you that you can decompose this class as P plus N, where N is some effective divisor, you know, maybe R divisor, but certainly effective. So this is somehow the negative part. And then you have this part P, which is nef in codimension 1. So nef in codimension 1, so this is pseudo-effective plus a bit better, so plus pseudo-effect, at least pseudo-effective on all divisors. So if you have a surface, then this decomposition is I decompose my pseudo-effective divisor in something which is effective plus nef. Okay? In higher dimension, this first part here is not nef in general, but you know, a bit better than just pseudo-effective. Okay? It allows you to go a bit further. And what I will do now is I'll show that in our situation, n is equal to 0. Okay? So I'll show n is equal to 0. So somehow this negative divisor part will not exist. And then the actual argument is more or less the same. You use some kind of decomposition, not for the tautological itself, but of its self-intersection. So there's some descending induction on the dimension of the bad loci which might appear. But the spirit of the argument is very much the same. Okay? So let me just show C equals 0. Now, how do I do this? Oh, no, I will show n equals 0. So I take C in X, general complete intersection of sufficiently ample divisors, general complete intersection of sufficiently ample divisors. So this is a curve, no, complete intersection curve of sufficiently ample divisors. And I can apply, so these are the assumptions to apply the theorem of Mechter-Ramanathan. MR would tell you that if I restrict my vector bundle V to C, this is going to be stable. And of course, since C1 is equal to 0 on X, well, the restriction will also going to be C1 equals 0. Okay? So in particular, V restricted to C is going to be nef. Okay? So I know this. So note that this means that if I restrict my tautological divisor so now I have the tautological divisor on the projectivization of this restriction. This is a nef divisor. Okay? So this is nef. Okay. Okay, so I restrict to this, and then so you see, I'm interested in the tautological class. I restrict to this kind of subvariety where I know a bit more, and let me also restrict these two other guys. Okay, so restrictions P, C, and C. And in view of the generality of C, this is still going to be somewhat effective. And this is still going to be someone which is at least pseudo-effective, actually a bit more, but I won't need this. Okay, so I got this. And now I compute. Now I compute. Okay. So the rank, I will note by R, that's the rank of the vector bundle. And now, so you have this Neff divisor here on this guy, and you take its top intersection. Okay, and now you want to use your decomposition. Okay. Okay, so this is a Neff divisor and this is an effective divisor. So if I compute this intersection, this is certainly non-negative. This is a Neff divisor and this is a pseudo-effective divisor. So still, this intersection is going to be non-negative. And this I also know. This is C1 of my vector bundle. Okay, so this is 0. Okay. So what do we obtain? We obtain that this intersection here, this is equal to 0. Okay. And now, of course, you see there's some slight issue because, you just have stability maybe for V, but, up to some technical modification of the statement, you can apply it to the lemma to the situation. So apply lemma to get that this intersection number being 0 means that this divisor is just 0. Okay, so NC is 0, but then it's not, since C is a general curve, this will tell you that N is already 0. Okay, and that's it. Okay, so I think I'll stop here.